Hi, welcome to Mathematical Statistics. I'm Mark Ledbetter. This is video 1 of lecture 1, and lecture 1 deals with the section on normal approximation for discrete distributions. In our textbook, this is going to be section 5.7. All right. So in order to do this, we need something called the continuity correction. It allows us to approximate a more continuous distribution using a discrete distribution, because what we want to do is we want to use the normal distribution to estimate these two discrete distributions, the binomial and the Poisson. So here's the basic concept. We have a binomial distribution, and that, if you remember, is the sum of Bernoulli random variables. And so if xi is a Bernoulli random variable, then it can take the values of 1 or 0, 1 if we have a success, whatever that is, our category of interest, and 0 if we have a failure. So for a Bernoulli distribution, mu is p, the probability of success, and sigma squared is going to equal p times q. And notice that we're not interested when p is equal to 0 or 1, because these are trivial cases. P equals 0 implies that sigma squared is equal to 0. P equals 1 means that sigma squared is also equal to 0. That means there's no variation. That means we really don't have much need for statistics in that case. Okay? So we're interested when p is between 0 and 1 but not equal to. And then if you remember, we sum up the xi's, I equals 1 to n, and the result is a binomial distribution with sample size n and probability of success p. Okay? Now, with the central limit theorem, what we do is we could call it z. This is usually we take the z for the standard normal. So I'll take w, and w, we're going to take y minus mu of y divided by sigma of y. Now remember, for a binomial, the mu of y is equal to n times p, and sigma of y is equal to the square root of npq. Okay? So that's the properties of the binomial that you need to know. And so we have y minus np divided by square root of npq. Now, in order to get this other expression to the right of the equal sign, we multiply the top and the bottom by 1 over n, or we divide both the top and the bottom by n. However you want to look at it, or we factor out n out of both the top and the bottom. They all result in the same thing. Y over n is x bar. Np over n is p. And then 1 over n square root of npq is equal to 1 over square root of n squared. And I'll just put the npq up here. And this is equal to the square root of npq over n squared, which is equal to the square root of pq over n, which is exactly what we have here. And so as n gets very, very large, the distribution of w approaches the standard normal. Now, for large enough n, then y is approximately a normal distribution with mean np and variance npq. And w is approximately a normal distribution, a standard normal distribution. That's the idea. Now, this is again for large enough n, whatever that is. Okay. So here's the rationale. The discrete distributions only have mass or probability at the points in the support of x. Everywhere else, the probability is 0. So in between these points that x can take in the discrete distribution, there is no probability. On the other hand, a continuous distribution has absolutely no mass or no probability at any point in their range. It's always 0. In order to have any probability, we have to have an area under the PDF, area under the curve of the PDF, okay? So in order to resolve this conflict, we're going to rewrite a probability function statement for the discrete random variable as a range of values, and then that will still be a true statement, but that will allow us to do the transformation to a continuous distribution. So what do I mean by that? So let's take a look at this. So it's true that if I look at this will be 0.5, this will be negative 0.5. So the probability in this case that u is equal to 0 is equal to the probability that u is between negative 0.5 and positive 0.5. That's true because there's no probability anywhere except at 0. And I haven't run into the next point yet, which is at 1. Right? So what we do is we just split the difference between each of the points, and then we do the same thing we did in introductory statistics. We write a histogram, basically. And so this is the concept of what we're doing, is that we split the difference between all the points, and don't forget you have to go above the last one and below the first one. And then we pretend that, well, it's that the probability is distributed or evenly distributed across that area, or not evenly distributed, but distributed across that area. And so this is going to allow us to use a normal approximation for this, because now we have a range of values. And these are really, they are identical to each other. They're equal, those probabilities. So what are we going to do? Well, first we need to look at the guidelines. And these are the minimal guidelines. Just because you meet this guideline doesn't mean you're going to have a good approximation. Again, the bigger n is, the better. And also, the closer p is to 0.5, the better. Why? Because that's going to maximize these two values. So if you look at this, NP, this is the number of successes. And this is going to be the number of failures. And so this means that we need to have at least 5 in each category, so n has to be greater than or equal to 10 to use this approximation. We're going to violate that and see what happens. Okay? But just because we meet this approximation, or these guidelines, doesn't mean that our approximation is going to be very good. So the bigger n is, the better the approximation. Okay, so the continuity correction for discrete distributions, we're going to let x be a binomial distribution here with n and p. Then, as I said, the probability that x is equal to k is the probability that x is between k minus a half and k plus a half. So if we look here, if k is equal to 0, then that's what we've done here. 0 minus a half is minus 1/2. 0 plus a half is plus a half. If k is equal to 1, then we'd have the probability that k is between 0.5, or x is between 0.5 and 1.5. Okay? So that's what we're doing. We're adding and subtracting the 1/2 as the continuity correction. Okay? So we've done that. You'll notice there's an equal sign here, not an approximation. This is going to be true. Now, and here I can put an equal sign. All right. And here I have, now I'm transforming. So I've taken this new value, I've subtracted the mean of x, which is NP, and I've divided by the standard deviation of x, which is NPQ. I do that with x and I get W, okay? And then I do the same thing with k plus 1/2. And then I can say this is approximately the probability that k minus 1/2 minus NP over square root of NPQ. And so z is between these two values, and z is a standard normal. Okay, so k plus 1/2 minus NP over square root of NPQ, NPQ. Okay, so here's the approximation because z is a standard normal. So in this, x is we can approximate x with a normal distribution, mean NP, that's mu, and sigma squared is NPQ. And W then, with this transformation, is approximately a standard normal distribution. And, so Z is the standard normal. Okay? So let's do an example, see how this works. So we're going to let x be a random variable that describes the values of a four-sided die. So the probability that x comes up with a 0, 4, 6, or an 8. It's a four-sided fair die. So then, this is given information, by the way, all of this. Then x is, of course, a uniform distribution, discrete, that can take values between 0, 4, 6, and 8. It can take those exact values, not between. It can take any of those four values, and that's it. So the uniform distribution, the probability of any of these values is going to be 1/4 because the number of elements in x is 4, okay, where x is 0, 4, 6, 8. Now, we're going to roll the die 4 times, and we're interested in the number of times that the 4 occurs, okay? So we're saying that u is going to be x1 plus x2 plus x3 plus x4, and I'm telling you that it's a binomial. But up here we said it was uniform. X was uniform. And the sum of uniform is not a binomial. In fact, it's not a uniform either. If you remember, we added two uniform distributions and we got a triangular distribution. We subtracted 2, we got a different triangular, a rotated triangular distribution. So what's going on here? Well, x is this, and the confusing part is xi is, they are Bernoulli with 1/4. Why is that? Because xi is now a 0 or a 1 if x is equal to a 4. If x is not equal to a 4, it's 0. And we're going to add up the number of times that a 4 occurs. So this value is going to be a 0 or a 1. This is 0 or 1, 0 or 1. If we're throwing the fair die, the probability doesn't change, and they're independent trials, constant probability. There's 2 possible categories. You say, well, there's 4 ways that there's 4 values that x can take. True, but we're saying we're only interested in 4, and then we're grouping these other 3 together as not 4. So we've just made it 2 categories. And so we do that a lot in statistics. Okay? So these xi are Bernoullis. When we add them up, Bernoullis become binomial. And mu of u is np, which is, there's 4 times a fourth, which is 1. And sigma of u, squared of u, is npq, which is 4 times 1/4 times 3/4, which is going to be 3/4, which is 0.75. All right. So and here is the distribution for u. Okay, so I've given it. It's not symmetric, notice. Not a symmetric distribution because p is not 0.5. All right. So we want to find the probability that u is 0 and the probability that u is 4 using the normal approximation. Okay? So our requirements are the first thing that we should check. And we see that np, which is equal to mu, is equal to 4 times 1/4, as we said, is equal to 1. That is not greater than or equal to 5. So we do not meet that one. And then nq is equal to 4 times 3/4, which is equal to 3, which again is not greater than or equal to 5. So we are not meeting the requirements. We should not do the approximation. I'm going to anyway to show you how it turns out. Okay. So we want to start off with, and I'm going to zoom in to make this easier for me to write, u equals 0. Is equal to the probability. We're going to subtract a half and add a half. So we're going to get negative 0.5 to positive 0.5. That's an equal sign. I also have an equal sign if I'm going to say negative 0.5 minus mu, or np, which is 1, divided by the standard deviation, which we said was 0.75. And I take the square root of that. Yeah, the variance was 0.75, so the square root is that. And then we transform u the same way. We're going to get w, and then we have plus 0.5 minus np over the square root of npq, which is 0.75. And then this is equal to the probability that w is negative 1.73 between that and negative 0.58. Okay. Now we come to the approximation sign. we're going to change this to a z so that we can use the standard normal. 1.73 z negative 0.58, which is then equal to phi of negative 0.58 minus phi of negative 1.73. Now we go to the normal distribution table, and I need the negative. So the first table has, the first table has the positives. So, and these are positive z's. And so we'd have to subtract to get the negative. Or we can get it directly from the second table. This second table has this, and you'll notice that's equal to phi of the negative z. So I need phi of negative 0.58. So 0.5, and I come all the way across to the next to last 1.2810. I also need phi of negative 1.73, so I can come over 0.0123.0418. Now, I'll transfer that over to here, to our slide we're working with, and this is going to be 0.2810 minus 0.0418, which is equal to 0.2392. Now, what should it be? It should be 0.3164, so this is way off. Okay, like a third of the way off, so that's not a good approximation. Now, let's look at u equals 4. So we've took the minimum value of u that it can take, and now we're taking the maximum value. Again, we're going to subtract half, so that's 3.5, and add half, so that's 4.5. And then we're going to transform, and so we're going to have 3.5 minus 1 over square root of 0.75. We're subtracting the mean, dividing by the standard deviation. This becomes w. This will be 4.5 minus 1 over square root of 0.75. And this will be the probability that w is between 2.89 and 4.04. Okay. Now for the approximation. We're going to say that's approximately equal to z between these two numbers, which is equal to phi of 4.04 minus phi of 2.89. Well, there's a problem. 4.04 is not in our table. So I want to give you the instructions on what you do in this case. Okay, so interesting, we go up to 3.49 on this side. And so remember that this is 3.49. This is the probability above that value. So at 3.49, the probability up here is 0.0002, so the probability over here for phi is 0.9998. So it turns out that if z is greater than or equal to 3.5, phi of z is greater than or equal to 0.9999. So use that. If z is less than or equal to negative 3.5, phi of z is less than or equal to 0.0001. So since we've got a positive 4.04, we're going to use this 0.9999. And then we have a 2.89, and we can find that. We'll use the first table because it's a positive. So 2.89 is the next to last one, 0.9980. So we're going to use 0.9999 minus 0.9981, and that is equal to 0.0018. Now, these are the approximations. How close is it to the real? This is more than 50% below this. And this one is about 30-some% below that. How do I calculate that? Well, why are the approximations so poor? Because NP is not greater than or equal to 5, and NQ is not greater than or equal to 5, both of those. And so how do we calculate percent error? So for the probability of u equals 0, it's always the same. the percent error, we have to know the actual. So we take the actual minus the estimated. Okay. Or actually, we should probably do it in reverse. Estimated minus actual over actual. And then if we get a negative, that means we have a smaller estimated value. If we get positive, we have a larger. So for this one, our actual, our estimated was a 0.2392. Our actual was 0.3164. So divided by 0.3164 is going to give me a negative 24.4%. Okay, so I'll 24.4%. So we're now error, we usually take the absolute value. The negative tells us that we're below. So 24.4% error. So that's not good at all. Like I said, nearly a third. So how about for u equals 4? So we'll take estimated minus actual divided by actual equals, and we'll take the absolute value. And for this one, we have the estimated was 0.0018 minus the actual 0.0039, and then divided by 0.0039, and this is negative 53.8%. So 53.8%, so a little more than half off below. Okay, so we underestimated. This is a very bad approximation. Okay, so that's it for this video. We'll come back and pick up with example 2 and 3 in the next one. Please make sure you update your formula sheet with what you've learned today. Let's see, and after each video, you want to look at all of your sheets that you have and see if you need to update them. Okay, formula sheets, distribution sheets, transformation sheets, those sorts of things, so that you can do well on the test without having to look up the information. If you have any questions, by all means, come to virtual office hours. If it's past that or you can't do that when you need the help, then by all means email me and I will try to help you to the best of my ability. Just you don't want to wait till the last minute to email me, because I may not see your email in time to get back to you. So so make sure that you do your homework and do your work ahead of time, so that you're not in a crunch. All right, we'll see you next time. Take care.